So yeah, so the problem in sorting, like you have a sequence of numbers. So like for example, let's say 12. It's, yeah, it can be any sequence of 1, 13, 14, minus 1, 8, 20, like that. So you have a sequence of numbers, and so they are unordered. So this sequence of numbers this is an unordered sequence of numbers. So we would like to, what sorting algorithms does is, so we take this list and we want to order them. So it's put it simply minus 1 in this case, 8, 13, 14, 20. This is a sorted sequence, sorted or ordered sequence of numbers. Yeah, I think this is okay. So this is the problem that we have at hand. So how do we take a sequence and which is unordered and make turn it into a sequence which is either ascending order or descending order. That's the problem. So this is a very well studied problem, and it has wide applications in many places. So because sorting is the most usual thing that we do when we try to analyze things and rank people, things like that. So like for example, in JEE, maybe 1 lakh people students could be giving an exam. We want to sort them in the decreasing order of their marks, for example. And there are many approaches for sorting. So we'll just look at maybe a couple of approaches in today's class. The first approach is what is called as a bubble sort approach. So in bubble sort, what we do is, like for example, if the list is something like this, maybe one of you can give a list of 5 numbers in the chat box so that I can pick it up, maybe 5 or 6 numbers in the chat box. 42069. Huh? Okay, I use 42069 because it is easy for me to write on the screen. So 42069. So in bubble sort, what we do is we start from here. We start from this list, and we compare, to start with, we compare these two elements 4 and 2, and we will see that 4 is greater than 2. So there is, so what we do is we swap them. So we swap 2 and 4, and we get a list like this. So you compare 4 and 2, and so 4 is greater than 2, and then in the next iteration, so you compare these two. You compare 4 and 0, and again 0 is less than 4. So we kind of swap these two elements. So we get 20469. And then now we compare these two elements 4 and 6. And so 6 is greater than 4. It remains the same. There is no swap operation happens. And then now we compare 6 and 9, and again like 9 is greater than 6, so the list remains the same. So now at the end of this is what is called as one iteration. Let's call it as iteration 1 of bubble sort. And so in iteration 1, what happens is as there's already a good conversation going on in the chat box. So the largest number bubbles up to the last position. So So that's what happens. So you kind of, you take the thing, so you keep bubbling up the largest number to the last position. So here 9 turns out to be the last at the end of uh, this whole thing. So 9, the element here at this position, the element here, this is the largest element. This is iteration 1. So actually, so I have a very good story here. So when we were studying, BTech, back in those days, we used to learn Fortran and Pascal in our as our programming language courses. And so I thought I was so excited to go to the lab, and thought I figured out an algorithm for sorting the numbers. And I just did one iteration, and then when I kept giving input, I realized that all I am doing just by swapping is just being able to bubble up the largest number. It's not really sorting. So, and then I felt great. So now I understood the issue. So all I have to do is, in the next iteration, I have to ignore the largest the element here, and then iterate over the rest of the 4 elements. So now what we do is, so in the second iteration, so in iteration 2, so what we do is, we look at 4206, and we ignore 9. 9 is there, but for our purposes, no, this is not there. In iteration 2, 9 is not there. And then we apply the same process. We compare 4 and 2. Let me use so we compare 4 and 2. Again, no, 4 is, oh, no, sorry. I think you should correct me, guys. So at the end of, yeah, so it is, thank you. So at the end of iteration 1, the state of the array is this. And so 9 is, we don't consider 9. So now we compare 2 and 0. Like now when we compare 2 and 0, so we end up doing a swap. And so let's say I put a star whenever swap is required. Here also I put a star. So here I don't put a star, I just put a dash, saying here also I put a dash saying there is no swap required. Or I can even use a different color to indicate. So here, let's say I use this dash, meaning that no swap has happened here. Great. So now, so you compare 0 and 2. So you have 4, you have 6, and 9. It is, no, you don't need, we don't consider 9 here. We just leave it as it is. Okay, so that's the reason I will not write 9 here. And then we compare 2 and 4. They are in order. So here there is a swap required. But here if you see, no, 0 to 4, and you compare, yeah, it remains as it is. And then now here you compare 4 and 6. You don't know swap is required. So again, if you see, so here there is no swap required. Here there is no swap required. Right? So now at the end of this algorithm, at the end of second iteration, what we have is 6 is the one which got bubbled up. And now what we do is we go to iteration 3. In iteration 3, so the state is like this: 0, 2, 4, 6, 9. And we don't look at these two elements. They are in the right positions. So again, we come down here, we compare these two. There is no swap required, so it remains the same. And then again, we compare 2 and 4, no swap required. It will be 0 to 4. And so once we make an iteration of once we make a loop, an iteration in which no swaps are being done, then that means the array is already sorted. So after I3, it is not necessary for you to go to iteration I4 or I5. It's not necessary. So this is a basic bubble sort algorithm. And so what I would like you to do in today's class, in today's lab session is solve this bubble sort algorithm. Okay, so these are the things I want you, I will explain to you basic sorting algorithms. I would like you to implement these sorting algorithms in today's lab. Hmm. Oh, this was there in chapter 9. Okay, good, good. So did you implement? Okay, awesome. Is it quick sort or is it? I thought that was selection sort, not bubble sort. Okay. Okay. So anyway, so uh, yeah. So this is, are you all with me on this basic bubble sort algorithm? The bubble sort and insertion sort are kind of different, little bit different. Great. So yeah, so please, in today's class, I would like you to implement this algorithm. Specifically, I would like you to implement this last optimization, where when you make an iteration and when there are no swaps happening, then that means the remaining list is already sorted. Like for example, in this iteration, since 0 to 4 is already sorted, what happens is no swaps happen. So when there are no swaps happening, then then what happens is then you automatically terminate. It is already in a sorted order. Are you all with me here on this last idea? Yeah, you should terminate after I3 because if you look at the leftover prefix sequence, if you think of 0 to 4 as a prefix sequence, then it is already sorted. So the idea is in bubble sort, maybe to summarize bubble sort is this is the right way to summarize. Uh, so the idea essentially is bubble up the largest element to the last index, to the last position, to the last index. Okay. Number two, sort the rest of the prefix array. Sort the rest of the prefix array. So does this make sense? So like for example, if this is your state of your array, you start with this array. So this is the initial state of the array. Let's call this initial state of the array as A naught. So what we do is in the A1 state of the array, so what happens is the element that is present here, it will be the largest element. And what is this? This is the prefix. This is the prefix array. And you want to just recurse on the same prefix array. And one important idea is, let's say, just to re-emphasize what is being already told, let's say the array is 2, 4, 7. And when you compare 2, 4, 7, 8, when you compare 2 and 4, they are no, they are no swap is necessary, and then you compare 4 and 7, no swap is necessary, and you compare 7 and 8, so no swap is necessary. So 2, 4, 7, 8 as it is. So when there is no swap, we kind of mark this as this. So when there are no, so you can see that there are no swaps are there. When the array is already sorted, then no swaps will be there, in which case we declare the array as sorted without going for next set of iterations. So here, let's say in this example, after you bubble up the largest element to the last position, so if you, let's say, this prefix array is already sorted. So it turned out to be sorted. And then when you make one more iteration, you will observe that there is no need for any swaps, in which case you stop the bubble sort algorithm at that place. Are you with me in here? So here there are a couple of ways in which you can write the bubble sort algorithm. You can write the bubble sort algorithm in an iterative fashion or in a recursive fashion also. So I think I would suggest, actually, in order to get good experience, you can kind of try to solve this problem in a recursive fashion and in an iterative code. When you write an iterative code, you kind of require nested loops. And if you write a recursive code, then you will have a loop followed by a recursive function. Something like the recursion may look something like this. The recursion may look, let's say, you want to do bubble sort, and the function signature may look something like int a and int size. Okay, so this could be your thing. So what do you do? What is the base condition? If size is equal to 1, you don't need to do anything. You just kind of return. But on the contrary, if I'm just giving a recursive version of the code, you should try to do the uh, that is size of the array. Okay. So and then so after that, what you can do is maybe you can have another function which kind of says bubble up, which where you call bubble up a and you give size. This will kind of bubble up the max element into the last index, and then possibly you can call again. What should be the call, recursive call here? Can someone tell me what should be the recursive call? The recursive call is a size minus 1. That's it. Are you with me here? The function type is void. Are you all with me here? So there is an iterative version, then there is a recursive version. In today's lab session, I would like you to try both. Write an iterative version and write a recursive version. So if you kind of think about in terms of, this is something interesting I would like to point out here. In terms of time complexity, both the iterative version and the recursive version, they will have the same time complexity, the number of operations required. But then there is a overhead involved in calling a function. So you have to do many things there are many under the hood things happen when you make a function call. So this is called as overhead. Yeah. So because of that, when you sort million numbers using an iterative version versus using a recursive version, you will see that the iterative version will be much faster than the recursive version. Actually, let's do this. Let's have this fun problem for you. The fun problem for you is this. Okay. So code bubble sort in two ways. So I keep apologizing for my handwriting, but I can't help it. In two ways. One is recursive version, the other is the iterative version. on for different inputs, okay, for varying sizes of input, compute the time, not the compute, measure the time required for sorting and plot them. Like for example, so this is the sizes of input. Let's say the size of the input is, you start with 1 lakh, okay, not 2 lakhs, like that. So you kind of keep increasing the input size and see how the time varies for the iterative version. You may have two curves, one curve for iterative version and another curve for recursive version. I don't know which curve will be what. I can maybe TS will provide some input on how to measure time. On already our Kishore is there, na? So he will also help us in helping us out. Okay, so yeah. So are you all with me on this question? Pramod, so there is a problem when you do time dot slash a dot out. There is lot of other things when you do, no, like for example, reading the input and so all those things will come into will be part of that a dot out execution. But we don't want to, like for example, guys, I want you to pay attention to this. So number one, uh, read read array, sort array, and maybe, like depending upon the case, you may want to dump the array, a sorted array or whatever. When you just do time a dot out, what happens is uh, so one this time and this time everything will be included. But what we want is we want this only. We want the time for this, only the sorting part. In order to do that, we have to take a kind of a timestamp before and after the sort. But I want you to, how many of you are with me on this question? There are two ways of coding bubble sort. One is a iterative version, the other is a recursive version. I want you to code the bubble sort in two ways, and then measure the time for different input sizes, and then plot it and see how it works. It will be very fun exercise to do. Merely, instead of merely coding, May has this question. In this, only the biggest number is given. So May is trying to say, can we try to find min and max in the same iteration? I am not sure. I mean, maybe it is possible. Maybe it's not. Not sure. So few observations here. Uh, Karthik has a very good question. Recursion always involves function overhead. If so, why recursive methods so highly sought after in computer science? Some problems are very difficult to think if you don't use recursion, Karthik. Very, very difficult to think if you don't use recursion. Especially maybe in your uh, algorithms course, you will learn about dynamic programming problems. So yeah, so there are many. What kind of intuition you are looking for, Kishore? I mean, how do you want to express the same problem in terms of the sub problems? And I think when you try to they are usually harder to think about. Maybe you are really thinking about hard problems. But for like for let's start with I think depending upon the problem context. Okay, so how do we come to know when to apply recursion? Good question. Yes, I mean there are no many times. It depends on how you. It comes with experience. It comes with experience, I would say. So you write more and more programs, you will see Sometimes, usually, you will see that when things gets harder, you want to kind of think recursively. The way you want to solve problems in mathematical induction, you want to reduce a problem to subproblems. So yeah, so there is this question, whatever you can do using recursion, you can do using iterative algorithms. Uh, what is nested recursion, Mukundan? Yeah, there is. Okay, so I want to move on and want to make a few remarks. So here in the case of bubble sort, what is the best case time complexity in terms of where the time is the number of comparisons that we make? So comparisons, best case, the number of comparisons that we make in the best case, it is n. Like if the element is, if the data is already sorted, best case time complexity is n. We make n comparisons. I don't want to use big O notation, etc., because you will learn what it means exactly in a later course, in possible in data structures. And what is the input which induces this best case time complexity? That is like if the array is already sorted. So if you have an array where you have A1 is less than A2 is less than A3 is less than or equal to AN, then this is the case where you get the best case time complexity. And what is the worst case time complexity? No, the best case time complexity is n, because if it is all sorted, you just make one pass on it and you figure out that there are no swaps are required, and then so you settle there. And the worst case time complexity is, this is the worst case time complexity is, like this is n square. So when it is approximately n square, I would say, when the elements are not sorted, or in the opposite, when they are in the descending order, like A1 is greater than A2 is greater than A3 is greater than so on up to AN. So then what happens is in the first iteration, A1 will bubble up to the last position and it requires n minus 1 comparisons. Please pay attention here. In iteration 1, you require n minus 1 comparisons because you compare A1 with A2, you swap. You compare again A1 with A3, you swap. So it requires n minus 1 swaps, comparison and swaps to bubble up A1. And then you require, like n minus 2 comparisons and swaps to bubble up A2, because A2 will be at the, so on and so forth. So you have, so finally A1. So the total number of comparison operations is n minus 1 plus n minus 2 plus n minus 3 plus, so this is n minus 1 plus n minus 2 plus so on up to 1. So this is nothing but like n into n plus 1, but here n is nothing but n minus 1. So the time complexity is n minus 1 into n by 2. But as we said, like n square term is there that kind of dominates. So because of that, we kind of say approximately it takes n square time. Are you all with me here? Is bubble sort clear? Okay. So now I will introduce you one more sort, and after that, I think we will break for today. That is merge sort. And so this is, yeah, Kush, that is the, so you have to figure that logic. So I want you to think about it. It's a good question, Kush. That is, so Kush is asking like, how do we know that that we don't need to go to the next iteration, you have to use some kind of flag to figure out if there is a swap happened or not. And based on it, you have to figure out whether you have to go to the next iteration or not. Yeah. No, that's not. We making another function call to check if it is in order. It's not necessary. It's unnecessary. I mean, you are making an unnecessary pass on the data. It's not good. You think about it. Okay, so there are already some hints given. Either you can use a counter which counts the number of swaps that are done in an iteration, or you can, like for example, if we go, one simple technique is at the beginning of iteration, you maintain a swap count variable. Swap count is equal to 0. So whenever you do a swap, you do plus plus swap underscore count. So here you do plus plus. Whenever you do a swap, you do swap underscore count. So here you don't do it. Okay, so here also you don't do it. And then after that, when you're going to iteration, when you're going from iteration 1 to iteration 2, you should make the swap count variable again equal to 0. And before you move from iteration 1 to iteration 2, you should check whether the swap count is 0. If the swap count is 0, then you don't need to go to the next iteration. So something like that you have to do. Okay. Yeah, the number of comparisons. Yeah, it's true. Okay, so question for you. So do you want me to go to the Metasort, or you want to go ahead and code the bubble sort and try out the two versions and work on it in today's lab? What do you want to do? Merge code. Let's do merge code. It looks like an equal split. Okay. Let's do merge sort, and then you can code merge sort also in today's class. That would be nice in the lab session. So Metasort is very simple. Like it's like if you have two stack of cards, and if you each of them are already sorted. Like for example, let's say there is one stack of cards. Let me put it this way. So they are already sorted. So let's say 4, 5, 10, 20, this is 3, no, 9, 12, 32, 43, right? So in this is one stack of cards which are already sorted, and this is another stack of cards which are already sorted. So now if you want to merge these two sorted uh, stacks, what would you do? What would be your strategy? So what's your strategy? You take you check 4 with yeah, you check you compare 4 with 3. You compare 4 with 3, and no, so 3 is the smaller element. So you so 3 will you move 3 to the new position. So here initially you have a position here, you have this something like this here. You compare 4 with 3, and then so now 3 got moved. So when 3 got moved, so what you should do? So now the stack pointer will now move here. So now you compare 4 and 9. So again 4 is smaller than 9. So what you do is you move 4 to the new stack, and then you move the pointer here. Are you with me so far? Are you with me so far? And then now you compare 5 and 9, 5 and 9, and let me use, like the latest, the current, the stack pointer, the current latest pointer, let me use a green for it. Okay. So, so this is what it is. So now when you compare 4 and 5 and 9, so 5 is smaller, so 5 moves up here. So this pointer will go down here. So we have this, and what do we do? So I will erase this and I will mark it as this. So this is how, this is where we are. So now you compare 10 and 9, right? And then when you compare 10 and 9, so 9 is the smaller element, so 9 will be here. And then you want to move the pointer here, and this is the old point. So like this, what we do is we compare these pairwise elements, and then we create a single list of sorted elements if these two are provided. Ha. So Vikram has a good question. Whether we need a separate Vikram, I will answer your question in a moment. So let's say for the sake of simplicity, you require another array to store the sorted list. Okay. Are you with me with the merge routine? This is if two arrays are already sorted, then you know how to merge them and create a new sorted array. Are you with me on this one? So what we are seeing here is how to merge two sorted arrays. How to merge two sorted arrays. And we store them in a new array. We store them in a new array. Okay. And we store them. This is a new array. Let's make it simple for us for the time being. Okay. So let's say this is array A, this is array B, and this is array C. Or you may want to call it as array AB, indicating that it is obtained by merging the arrays A and B. Okay. So the question for you is, do you require a 2D single, will you be able to do with a single loop, or you require a two-way nested loop to do this? Yeah, I think you should be able to do it with single loop. So think about it. Just this part, the merged part. So now, when will the merge will can work? If there are only two elements, if array A, if you take the case, if you have array A and array A has one element and array B has one element, can we just get away with the merge routine to merge them? Right? So it will give the, or if so the other case is array A and array B, like if this is empty also, it kind of works. You just have to put or the other way around. So array A, array B, so this is empty and this is 2. So in all these cases, the simple plain merge routine will result in a sorted list. So the idea now here is how do we use this merge idea to construct a bigger sorted algorithm. Okay. So what you do is you kind of write this routine, a recursive function. So let's say you want to do a merge sort. Okay. You are given an array A. You want to and you are given um what would be the right thing to do. So here we take low and so low means the lower index and high means the higher index. So what we want to do is we want to split this array A into two halves, okay, and we want to merge the lower half. So let's say you want to, so there is a segment of an array, okay, so where let's say we want to write a generic routine, so which says this is an array A and this is low and this is high, and we want to sort all the elements starting from here to here. Okay, this is what we would like to do, right? So the way we kind of do is, so we do merge sort. We want to do merge sort. So what we do is we divide this whole array into two parts. Okay, let's say we kind of say mid is equal to low plus high by 2. And then what you do is you kind of call merge sort on A, low, mid, and mid sort on A, no, mid, high. And then finally you want to do this. Yeah. So maybe so you want to merge the upper and lower parts. How do we do? Can someone help me here? Because if we are returning a, I'm just trying to think. You do a mid sort, and if you want to merge, yeah. Yeah, let's say whatever. No? So A is the array which you would like to sort. And let's say I just want to say A, low, high, indicating merge the two parts of it. And then yeah, you should, the logic for merge roughly I have explained. You have to figure out how to write the merge part. Mid you can compute, no? Yeah, this should be, see, I want you to be very careful here. So this is mid plus 1. This is mid plus 1. I want you to be very careful in computing this mid and all. Okay. So one thing that I would like you to kind of do here is when you do this whole thing, you may want to keep some kind of assert statement which kind of says what is assertion you would like to have. The assertion you would like to have is high minus low plus 1 is equal to the sum of the things that you are kind of sending. So what that kind of assertion you need to have. One more assertion I would like to have is that high is always strictly greater than or equal to low. So these two kinds of assertion I would like you to keep in this merge sort recursive function to see that you don't end up making mistakes in computing these boundaries. Are you with me here? What we are doing is we are taking a big array, we are saying sort the smaller array and then sort the bigger, no, sort the first half, sort the second half, and then merge them. And then what is the problem here? The problem, one more problem that you need to worry here is the base condition for the merge sort. You need to do. So that is no, the base condition. When you don't want, there should be a condition where you don't call the recursion. In the absence of that, you keep recursing forever and ever. Yeah, this is also wrong. So I think someone got it, got me. So this should be something like low, yeah, maybe low plus high by 2. Yeah, so this whole logic, it's screwed up, guys. So, but you understood the issue, the thing, right? So what we are looking for is we are trying to find a midpoint here, and we are saying sort this half and sort this half and merge them. What do we use to sort the separate halves? That is where recursion comes. You use the same Metasort itself to sort the separate halves. Exactly. Okay. So now so here I think I should stop here. Uh, so the reason is I made lots of mistakes in this code, and it's up to you to fix them. Okay. Are you with me here? So that you should find out the mistakes that I made, and you should find out all the mistakes, and you should try to figure those things out. Okay. Approximately speaking, so this is the whole array. Let me recap the whole intuition. This is the whole array you have. This is the array you would like to uh, uh, sort. So what is the idea? So sort, no, first half. This is the first half. Number two, sort no, second half. This is the second half. Number three, merge them. And how do you sort the first half? You recurse. How do you sort the second half? You recurse. When you are trying to sort the second half, you need to be, like the base address. So what do you want here? There are many ways of doing it. If you don't want to uh, if you don't want to use all this low and high business, there are ways to get around it. Where let's say the element here is no, a of n over 2. This is the element here. You can kind of pass a of n over 2 as the base address and think of this as a whole new array, and the size of this array as n by 2. Okay, so that also kind of works. Okay, so there are a couple of ways of implementing it. Did anyone get the idea that I'm trying to impress upon you? That in the previous case, we are sending the low and mid. So we are sending a, low, and high. This is a parameter that we are passing. Instead, what I'm saying is you kind of think of this whole thing as a separate array and pass a pointer to this, and the size of the array is reduced to n over 2. Yeah, so you have to pass. So these are two different ways of doing it, and so it's fun. I mean, you figure out which one works for you. The advantage in the second approach is the the number of parameters that you end up passing will be less. Yeah, you can always have iterative versions of recursive things, but Metasort is usually written in a iterative, in a recursive fashion. So Rajeshri, there is a very important thing. So there is a difference between binary search and merge sort. How many of you are aware of the binary search? I think most of you would be aware, since let me do a quick thing. So let's say if we have sorted array 1, 8, 9, 12, 20, 30. So if you want to search for an element, let's say 8, what you do is you go and compare 8 with this middle element, and you see that 8 is less than 12, so you kind of do a recursive search on the left half. Are you with me here? And and then what you try to find the midpoint here. The midpoint here is approximately 8. So you compare 8 with 8, and it turns out to be the case the same. So you say it is found. But let's say if you are looking for 25, then what you do is you compare 25 with 12. You know, no 12, 25 is present on this side. You ignore the left hand side, and then you try to look here. So now the question for you is, what is the difference between Metasort and binary search? Rajesh, you said they look similar. Is there any difference between the Metasort and the binary search? Very, very important difference, guys. If you know this, then they have different purpose. Of course, they have a different purpose. But in terms of computationally speaking, is there any important difference between these two? Yeah, one is for sorting, other is for searching. N log n log n, yeah, blah, blah. That's true. Binary search arrays are already sorted in ascending order. Binary search is much more less complexity. All these things are true. But yeah, Pramod has got it. So in binary search, so when you are looking for 8, so when you compare 8 with 12, so 8 is less than 12, so you discard this half. You discard this half. You don't worry about it. But in the case of merge sort, what happens is you have to work with both the halves. You are not discarding them. Are you with me here? Okay. It looks like you're all yawning. Okay. So this is very important when you try to do time complexity of algorithms. So this makes a huge difference on whether you're working on both the parts or you are discarding some part or the other. And that will have an impact on the time complexity of the algorithm. And some of you mentioned that the time complexity of merge sort is n log n, but whereas this is for MS merge sort and this is for binary search log n. Uh, so you know, the reason why this n is not coming down here is because we are discarding half in the binary search, but whereas in the merge sort we are working on both the halves. Because of that, this n factor is turning out. Are you with me here? How this small thing that discarding something is, we are able to shave off this factor n in the final time complexity. We didn't kind of look at why Metsort's time complexity is n log n in detail, but let's assume it is n log n. But the primary reason why for Metasort it is n log n, whereas for binary search it is log n, is in the binary search we keep discarding stuff. Because of that, we get that log n time complexity. That's true, Vikram. We need to keep recursing until we need two elements to be compared. Okay, I think I will stop here. I hope you're all with me in this today's lecture till now. Happy? Good? I hope you had good lunch also today. And no? Harry? Uh, so, okay, good. So, yeah, someone didn't have lunch, so should get something to eat. And awesome, guys. So now I think yeah, we should stop here. So my thing is I want you to code both bubble sort two ways, recursive way and iterative way, and merge sort. Plot the graphs for these three sorting algorithms for increasing input lengths. for that will be very fun to see this graph. If someone gets this graph by the end of today's lab session, send me a note. I would like to see it. Okay. Okay, then. So, and between lab 5, so if someone wants to take an extension, it's all right. Tell the TAs, and I think the TAs will tell you. I think they will be there, and yeah, so they will. Yeah, the graph time taken versus data size. That's what Pratyaksh. Yeah. Okay, guys. Then I'm signing off. Thank you. Have fun coding. Okay. Bye. See you tomorrow morning. Yeah, please go on to Teams. I think your TS will be there. They will